Hello everyone, I'm Wendy from Xilinx and I'm working on OpenAMP. And I'm going to introduce OpenAMP today. So we are going to talk about the OpenAMP project, the OpenAMP libraries, and what changes in the OpenAMP we are working on, and some near-term future improvement we want to do in the OpenAMP. So OpenAMP project overview. So what issues we want to solve in OpenAMP? So with today's sophisticated SOCs, there is often a need to integrate multiple runtime environments and with multiple operating systems. And this raises a lot of issues, such as the lifecycle issues, communication, and resource handling. For the lifecycle, there can be the following issues. The boot order of the subsystems, start one system from another, tear down one system, reboot, error, recover from error, and upgrade. Communication issues include how to pass messages between the cores and how to share data between the systems. And the resource handling includes the resource assignment and request the resource before you want to launch a system and release the resource after you stop it, and power management. So an OpenAMP is going to address the above issues and more in a standard way, and both through a standardization effort by MCA multi-core association and a open source project. So what's needed to be able to mix operating systems? We need a stand-up protocol so that the different operating systems can interact without any special adaptation. For example, on a shared memory-based system, it means a set of data structure and conventions. For example, the word I/O V-ring buffers. And a standard of APIs for operating system to interact with each other includes the following APIs: the low-level API abstraction for the underlying operating system and hardware, and lifecycle management APIs, messaging APIs, and other potential features such as the proxy capability to make a remote look like a Linux process, and others such as the RPC, remote procedure calls, and power management and debugging a remote system from the host system. And as the Linux is increasingly become the main operating system in a multi-OS system, so it is very important to have the upstream Linux support for the protocol and APIs. And which it is also very important, it is an open source implementation. It provides a very quick way to adopt the solution for your platform, and we provide reference implementation for the standardization. And so, what's OpenAMP? As mentioned, it includes both a standardization effort, which is driven by the MCA OpenAMP working group, and a open source project, which it is driven by Linaro Lite. So we are going to standardize the operating system interaction, in particular between Linux and RTOS bare metal in multi-core heterogeneous systems, which includes the shared memory protocol, lifecycle, and communication, and we are going to extend to more. With the open source implementation, we implement and test the new ideas, and we can do prototyping before standardizing, and we provide a business-friendly APIs to allow proprietary solutions. So what libraries the OpenAMP project currently provides? The OpenAMP source code is available from GitHub, and it is BSD license. Today it has 2 libraries. The OpenAMP library, it is for the protocol implementation. And today we provide implementation for API message, which is used for message passing, and Watch.io, which it is used for shared buffer management, and a remote prop, which is used for lifecycle management and resource assignment. And another library, libmetal. This is a library to provide low-level abstraction for device management, interrupts, I/O, and memory access. So the following slides will give a bit more details on the subcomponents covered by the OpenAMP. API message. API message, it is the protocol we used for communication between processors. So in AMP systems, the most common way for different cores to cooperate, it is a shared memory-based communication. And the API message, it is a shared memory-based bus to allow the communication between cores. So the API message in the OpenAMP implementation, it is on top of the Watch.io. And this diagram shows how the API message work. In a communication between the processors, one acts as a Watch.io master, the other acts as a Watch.io slave. And underlying the Watch.io, there is assigned shared memory between the 2 processors for the communication. And on top of the Watch.io, there are multiple endpoints. Each of the endpoints on one core can talk to any of the other endpoints on the other core by passing the message includes the source endpoint address and the destination endpoint address. Each communication needs a Watch.io master and Watch.io slave, and today there's no communication available between the 2 slaves. If you want these 2 cores to communicate, and then one core needs to be a master and the other needs to be a slave. The API message, it is on top of the Watch.io. And Watch.io, it is a I/O virtualization framework. It is used for parallel virtualization. And OpenAMP, it is used to manage the shared buffers. And on the master side, the API message, Watch.io driver, and the remote prop driver provides the Watch.io config ops as the front end. And on the other side, the API message driver and the remote prop as the back end. And if you want to know more information about the Watch.io, you can look on the website for the Watch.io specification, and also the implementation in kernel. So the following 2 slides are for the API message Watch.io flow. I will very quickly go through these 2 slides. So basically, the master side, you will get the buffer from a used V-ring queue, and then it copy its data and add the header to the buffer, and then enqueue it to a available queue, and then it will notify. Usually it is with a interrupt or a mailbox, notify the other end, and then the other end will get the buffer from the available reading queue and pass it to the API message endpoint callback, and then it will the queue after the callback finished return after the API message endpoint callback returns, it will the queue it will enqueue the freed buffer to the used queue so that the master can use it, and then it will kick the other side. This is the remote to the master. And the API message VirtIO implementation has some limitations. And because VirtIO itself has master-slave, and it relies on the master to start the communication, and also relies on the master to allocate the shared memory and initialize the rings. And if Linux kernel, it is involved in the communication, and the Linux kernel has to be the master side, as the backend it is not supported yet in the kernel. And the VirtIO status today only allows the master to report the status to the backend, and so if the backend restarts, it cannot notify back the master its status. So today there is no out-of-box support to recover the communication when the slave restarts, and the application or library built on top of it need to work around it. And the API message, it is mainly used for message to pass messages, and not for large data sharing. Because the default API message APIs will copy the data from application to the shared buffer, and the OpenAMP implementation, it provides a no copy support, but however on the Linux kernel side there's no such a support, and the shared buffer size is fixed at the reading initialization. And it is hard to mix the control service and the data service in the same pair of VirtIO rings. And besides the communication, and OpenAMP also provide an implementation for lifecycle management, which is the remote proc. The remote proc provides pass and load a remote system image, and request release the remote system resource, and the resource, it is described in the resource table. And also remote proc provides the API to do stop, start, stop, suspend, restore, shutdown, and error recover for the remote system. And so this is diagram shows the flow on how the remote proc to launch a remote system. So the application on the master side pass a image to the remote proc. The remote today we only the default image supported by the remote proc, it is ELF. User can of course can provide their own loader to pass their image if it is not ELF. And if there is a resource table inside, it will pass the resource table to handle the resources. There is one very important resource which is called carve-out. It is it will pass this resource and then figure out what memory it is required to load the firmware, and then it will load the firmware to that memory, and it will start the processor. This is a image supported by the OpenAMP application. It is an arbitrary application, and if you want the resource table, you can add the resource table as a session. This is some details of the resource table. I will just skip this one. So, and then besides the protocol implementation, we have a low-level abstraction, which it is the libmetal. It provides an abstraction layer across different OS and hardware platforms to provide device management, interrupt handling, and how to access the I/O and memory. It was previously there is a porting layer inside the OpenAMP, and then later on, and then we find that we think that the porting layer can be used independent to the OpenAMP library, and the OpenAMP libraries will focus to implement the protocols. So that's why we have this libmetal library. And this is the library's layers. How to get rid of this one? The bottom one, it is the hardware layer. And in the application, you will usually need to access some peripheral registers, and you will need to handle some interrupts, and of course, we will need to use the shared memory for communication. And on top of the hardware, and there will be a operating system layer. And then on top of this layer, there will be libmetal. It provides advanced handling, I/O, and device management, and other primitives such as locks. And on top, we have the remote prop implementation. And the remote prop provides some what.io config operation. And also, the remote prop also needs each platform to implement a driver so that it can know how to kick the other end, and how to get the device memory, how to get the virtual memory from the device memory, and how to start and stop the remote. And on top, there is what.io implementation. And on top of the what.io, there is API message implementation. And then just 2 weeks ago, 1 day ago, we talked about on top of these protocols, we should also provide some service layer, because we figure out there are quite some services which are interested by different vendors. For example, like structured buffers, that is the large data, and resource sharing. So we want to also provide some common implementation for these services to the application. And what changes we are working on? First of all, what's supported by OpenAMP today? It supports master-to-slave communication, and it supports message passing, and it supports Linux user space, FreeRTOS, bare metal, and we recently enable to build the libraries for Zephyr. And we support quite a few ARM processors, A9, A53, R5, and we also, because we support the communication between Linux process, so you can run OpenAMP on a x86. And so this is the changes we are working on. Enable Zephyr. As just mentioned, we enable to build the libraries for the Zephyr, and for libmetal, we can run the unit tests on the Zephyr QEMU Cortex M3 platform, and the Zephyr team, they are also porting the OpenAMP application, and they are doing some evaluation to figure out the code size and try to see what we can do to reduce the code size. And we are also working on to make the OpenAMP run on a resource limited, especially memory limited microcontroller. And code size, it is always a concern. And we are trying to reduce the code size in the OpenAMP code base. And this will include some restructuring work. We are going to decouple all the components so that the application can pick what they want from the OpenAMP in their application, instead of everything provided in OpenAMP all got linked into the application. And so some near-term future works. Testing, it is also important. It is very important. And but however, this is one thing which it is lacking in the current OpenAMP. So we are recently working on CI, and we will improve our unit tests. Metal has some unit tests, but OpenAMP, unfortunately, the unit test is broken. And we also try to launch some OpenAMP tests in the Linaro Lava Lab. We have a silence board recently installed there, and so we are going to run some OpenAMP tests. And then extend the resource management APIs in the remote proc to cover more than just memory and also the peripheral devices. And we also want to extend the VirtIO driver support. So because besides the VirtIO API message, we want to enable other VirtIO stack. And also we want to have some service to launch a application easier. For example, we are considering something like a bin format mixed daemon, so that on a Linux you can easily run a remote proc application, and you can send requests and receive response from the remote. And so so thank you, and I think we have some time for the questions.
Can I start? Okay. Yeah, it's very good presentation. Thanks. I'm just wondering, what are other participants in addition to Xilinx in the OpenAMP?
Yeah, so we have MCA group, and then there will be TIST.
Yeah. So currently involved, Xilinx, of course, Mentor embedded. We have TI involved. We have ST very much involved. We have Qualcomm and Linaro. One of the things that probably was clear here is that there's really two implementations. You have the kernel implementation, which is what it is in the Linux kernel, but we do have the Linux maintainer on board on the OpenAMP, so that when we do changes and add more features, always being backwards compatible, we can do those changes there as well. Other companies, we have a bunch of OS companies, and they're coming a little bit in and out. NAI is in there, Wind River has been in there, Mitrium, and so on. So it's a broad number of companies.
Great. So in the previous presentation, this ADAS platform, so it is OpenAMP also utilized in the ADAS platform?
Are you talking about
ADAS?
Go ahead. Okay, so what I showed you was a typical application or a platform that our customers would implement, but we do have design examples published by Xilinx. For example, we have something we call our base targeted reference design, which has a video pipeline. A53s are managing processing that video pipeline. The R5s are doing their own code, and data passing is all done via OpenAMP between the A53s and R5s. The R5s are also remotely started. by the OpenAMP infrastructure. We also have a software acceleration reference design, which runs FFTs on the 853s and R5s, and all the data from the R5 is passed over to the 853 via OpenAMP.
So the evolving OpenAMP will be reflected in the future ADAS platform, right? The evolution of the...
So Xilinx, we are not developing a ADAS platform. We work with our partners and customers to develop such.
Great, thanks.
You mentioned the code reduction work. Could you give a size expectation of where you want to get a bare metal version of this?
Right. The target it is as small as possible, right? and then we have some requirements to get it down around 4K. We are working on it to see how it goes.
That's API message only.
Yeah, API message only.
Right. Okay. Thank you.
Okay, so for a symmetrical processor platform, so which core is the first processor will be resetted? So, for example, for the hardware platform introduced in last session, so for this kind of multi-SoC cores, but they are different. So when your OpenAMP software is running, so which core is the first process to be initialized?
So OpenAMP, it doesn't, it's up to the user to decide which core. So OpenAMP is going to support on any processors in the operating system, and then user can decide which one it is the main processor, and then which one it is the co-processor.
Okay, so do you have any secret boot consideration for current OpenAMP software?
You're looking for some reference design, or?
No, I mean current OpenAMP software has any consideration for the secret boot?
But they start both statically. They start. So you are saying that boot independent.
No, I mean the security boot. Security boot.
Oh, security boot. Oh, okay, yeah.
Do you have any consideration for this?
Yes, we do. We are at least we are also expecting the OpenAMP, the secure world, the secure bootloader can also use OpenAMP into two cases. One, it is boot another coprocessor from the secure. The other, it is we are working on how to share data between because we do have this case like the Linux, and we want to have some message passing between our secure R5, and we are working on that.
Okay, thanks.
I think that's all time we have for questions.
Just very quickly, you talk about mailboxes using shared memory. Will it work with a FIFO-based mailbox?
Yeah. Okay. The OpenAMP, the mailbox today, it is mainly used by notification. So and then it will be up to the user implementation. It will work for FIFO-based mailbox. But however, our communication protocol currently implemented in the OpenAMP, it doesn't cover that. It is mainly just used for notification today.
So you'd have to extend it to do the
Yeah.
All right, thank you.